In this section, we're going to be talking about the coefficient of determination. If you haven't already watched the first video from Chapter 4, which discussed the linear correlation coefficient, relationships between variables, and how to create the least squares regression line, you definitely want to do that first. The coefficient of determination is the extension of those sections. What R-squared does is it measures the proportion of the total variation in the response that is explained by the least squares regression line. This R should look familiar. We've seen R in the past sections. Let's recall R is the linear correlation coefficient. Okay, and that was found, we did that in Statcrunch. It was found a different way using formulas as well. But that R, it could be positive or negative, and it told us whether there was a linear relationship between two variables, whether it was positive, it had a positive slope, negative slope, and told us exactly how scattered the data was, or if it was perfect. Now, if we simply just square that same R, I know that's lowercase and that's uppercase, but it is the same R. Now, if we just square that R, in other words, we're just making it positive, right? The R squared now is called something different. Once we square it, it's now called the coefficient of determination. In other words, this coefficient of determination is a measure of how well the least squares regression line describes the relationship between the explanatory and the response variable. The closer that R squared is to 1, the better that the line describes how the changes in the explanatory variable affect the value of the response. So this is an example of how I would expect you to interpret an R squared on a quiz or an exam. For example, let's say the coefficient of determination came out to be 99.99%. We would state in this order that 99% of the variability in the y, whatever y is for that particular example, you want to explain what y is, whether it be in the last example we did, y was interest rates, then you would put the word interest rates in here. We would say 99.99% of the variability in the interest rates is explained by the least squares regression line. So the only thing that changes is whatever your R-squared variable is. So you're going to be responsible for calculating this coefficient of determination and also given the linear correlation coefficient or vice versa. So it's important that you know how to interpret this, okay? So let's do one last example, or two more examples, I should say. One example of using the coefficient of determination, then we'll do one more example below this that will tie everything together from the whole chapter, and it'll be a good review of everything we learned in Chapter 4. So using this previous example, given the correlation of our calculated linear correlation coefficient, let's find the coefficient of determination. So from the previous example, the one about credit score, our linear correlation coefficient was negative 0.976. That's our linear correlation coefficient. Now, we're going to find R squared, which is the coefficient of determination. The coefficient of determination is going to be 0.976 squared. Now I do want to show you how to put this in your calculator because it does make a difference whether you do or don't use parentheses. We all know when you square a negative, you're going to get a positive. But look what happens if I don't use parentheses. You actually get a negative answer. And you should know that that is wrong. Because remember, squaring a negative number should always yield a positive answer. And it's because we didn't use parentheses here. What this is doing is order of operations. It's covering up the negative sign. It's squaring the 0.976 first. And then it puts, because exponents go before multiplication, and then it puts the multiplication of the negative 1 in front of your answer. It's almost like negative 1 times this number squared. So if the negative is actually attached to the number, you have to put it inside parentheses with it in order to get the positive version of that squared answer. So make sure you don't make this mistake. R squared will always be positive. So the coefficient of determination is 0.953. And if we were to explain this in a sentence, and we're going to use exactly how we would use it in this example up here, we start with this as a percentage. So in order to make this a percentage, we move this 2 times to the right, and we say 95.3% of the variability in Y. In this case, we're talking about the interest rates. Is explained by the least squares regression line. "95.3% of the variability, or in other words, the changes in interest rates, is explained by the least squares regression line." Okay, so here's where we're going to do one last example, and we're going to put all this information together from beginning to end. Okay, so let's say we have 1,375 pairs of data. So that actually means we have 1,700 individual pieces of data, because remember, this is 1,300 pairs. Okay, so it means you're collecting 2 pieces of information from one person. Okay, so for each pair, we have a mother and a daughter. The mother's height in inches was collected, as well as the daughter's height in inches. Okay, so we're going to keep that those pairs are together. This is paired data. Remember, it makes no sense to compare a mother's height, my mother's height, with somebody else's daughter. We want to compare a mother and her own daughter so we can see if one is a predictor of the other. Is a mother's height a good predictor of what the daughter's height is going to be? Which kind of answers the first question. Which variable do you think should be used as the predictor or explanatory variable? Okay, we're going to let X be the mother's height. And the reason why is because this is going to be the independent variable, and that's going to be used to predict how tall the daughter is. Okay, so let's keep going. Below is a scatter diagram of all of those 1,375 pairs. Clearly, we're not going to put this in Statcrunch because we're not going to type in 1,300 pieces of data. So I went ahead and copied the picture here for you. So this is what it looks like, and I would venture to say that this does have some relationship. It does appear to be linear. I would say it's moderate, and but it does seem to have a positive relationship. So we would call this a moderate, positive, linear association or relationship. Can you guess what the value of the R might be? Well, sure, we can guess. I mean, we don't know for sure. I definitely know it's not 1. It's not perfect. I definitely know it's not 0.9 because it's, I would say this is not super strong. So I would say that this is probably close to maybe 0.5 since it is moderate. Okay, it's just a guess. Even if the linear correlation coefficient is high enough to say we have a positive or negative association, why can we not say that the variables have a causal relationship? And the reason is because this is simply just an observation. This is an observation, not a designed experiment. We talked about the differences between observations and experiments back in previous chapters. Observations are simply just recording data that you've seen from the past. A designed experiment means you're changing or altering one of the variables and seeing what the response was because of that change. And we didn't cause any changes, so we cannot say that one causes the other to occur. So then I went into Statcrunch. Okay, so this is something you might see on a test, for example, because on a test you clearly don't have Statcrunch to be able to use. So on a test, I'll give you what the output, I'll just cut and paste it here into your test, and you'll have to interpret what all of this means. So here's the Statcrunch regression output for this particular data set. Let's read through what we know. So we decided that the dependent variable was the daughter's height, and the independent was the mother's height. It then gives me the linear regression line right here, the best fit line, the best least squares regression model. It gave me the slope and the intercept of that model. It also gave me the sample size, which is n. It gave me the linear correlation coefficient, also the coefficient of determination. So there's a lot of information here that we were able to get that we've already talked about in this chapter. So for number 6, it says state the linear correlation coefficient. R is 0.491. Then use table 2 on the table handout or table 2 from your book and determine whether there's a linear relationship. So table 2 from our book looked like this. Okay, and we go to an n of, there were 1,375 pairs, but you can see that our table only goes up to 30, and we'll talk about this 30 in future chapters and why most tables will only go up to an n of 30. But for now, since it stops at 30, and obviously our sample is much larger than this, we know that since the critical values seem to be getting smaller and smaller, we know that an n of 1,300 is obviously going to be smaller than this last number. And that's all that's going to be necessary in order to solve this question. So our critical value is going to be less than 0.361. So our critical value is going to be less than 0.361. So it's something smaller than 0.361. So if we were to compare these two values, no matter what this critical value is, no matter how small it gets, the R is still going to be bigger than any of those values in this range. And that's enough to be able to answer the question whether there's a linear relationship. Since our R, even though it's small, we had so many data points in our sample that it's enough information to conclude that it's bigger than the critical value, meaning we do have a linear relationship. So yes, there is a linear relationship between mother and daughter's heights. Okay? All right, so let's state the least squares regression line, which I have from the previous page. So let me try to pull both of those up together. Okay, right here. So from the previous page, we have the least squares regression model here in the box. And it says state that right down here. Okay, y equals mx plus b, so the slope for this case is 0.5417. I don't really have a rule as to how many digits to show. Usually I show 3. X plus, so y equals mx plus b. B is the intercept, which is 29.917. And it says state what X and Y stand for. So in this case, Y is the response, which is the daughter's predicted height. And then X stands for the mother's height. Using this equation to predict the daughter's height given a mother's height of 66 inches. So let's say there's a mother that has a height of 66 inches. What would you predict the daughter's height to be? So we simply just take this X, which is 66, and we'll plug it into our equation. And we'll find that the predicted height of the daughter is going to be, if you put this into your calculator, it's going to be approximately 65.7 inches. Let's say for a mother with a height of 66 inches, her daughter's actual height is 67 inches. So the daughter's actual height is 67, but as we set up here, remember her predicted height with the y hat was only 65.7. So she's actually taller than what was predicted. So it says compute the residual. Now remember, by definition, residual is equal to actual minus predicted. So in this case, residual is going to be 67 minus 65.7, which is 1.3 inches. And it is positive because she is above average. Let's interpret the slope. Remember, this number right here was the slope. This was our M. So interpret this into a sentence. So I like to always look at the formula when making my sentence. If I know that the slope is positive 0.5417, then that means for every one change in the X, so in other words, for every one change in mother's height, you're going to expect the daughter's height to go up by this many inches. For every one additional inch of mom's height, expect daughter's height to increase by 0.5417 inches. Interpret the y-intercept. Remember, this is the y-intercept up here. Remember, it's y equals mx plus b, so this is the y-intercept. So we're going to use 29.9 in a sentence. So let's again look at the graph. So this was mom's height, and this was daughter's height, right? And they were positively associated. So this point right here is 29, according to the y-intercept. So this is saying when mom is 0 inches tall, we would expect the daughter to be 29 inches tall. But that doesn't make sense. In this case, the y-intercept is not appropriate. Mom cannot be 0 inches tall. State the coefficient of determination. The coefficient of determination will be r squared. And according to our data down on this previous page down, oh, that's the wrong example right here, sorry. Here's the data from the previous example. It said r is 0.490, and when we square that, it already gave us the r squared, which is 0.241. So r squared is 0.241, and use it in a sentence. So we're going to have to make this into a percentage, and we would say 24.1% of the variability in Y. In this case, Y is the daughter's height. So 24% of the variability in daughter's height is explained by the least squares regression line. What are some other variables that we might want to include in our analysis that obviously were not included here? In other words, what are some other predictors of what the daughter's height is going to be other than just what the mom's height is? Well, dad's height, that would be one. What are some other ones you can think of? Siblings' height, birth weight, any mutant genes. In other words, they can be a little person or somebody that is very, very tall in a mutancy type of a way using genetics. And there's obviously lots of other ones as well. Let's see how many other ones you can come up with.